Hello everyone, welcome back to this channel. So in this video, we're going to look into IGCSE Physics Chapter 4, Turning Effect of a Force. So in the previous chapter, the force is something that we focus a lot on. We learned the formulas, we also learned the different types of force available, like contact force, gravitational force. Whereas in this chapter, we are more going to look into how a force can be used to create a turning effect. So in this chapter, a key term that you need to know is called moment. Moment is basically defined as the turning effect of a force about a pivot. Meaning, if you say you have a lot of moment here, means that you are creating a big turning effect. And what about the keyword pivot? And the definition of pivot is the fixed point about which a level turns. To give you some examples, the pivots on the door would be the hinges, because this is the point which the door will turn. And whereas the second example is a seesaw here, and in the middle of the seesaw, there's usually this thing. That's the pivot, because that's the point which the level will turn. And here we have three different factors which affect the moment of something, of a force. The first one being the magnitude of the force. If you apply more force, you're going to have more turning effect. And that's the first factor. And the area, the place which you apply your force is going to be able to affect the moment as well. And the further the force is away from the pivot, the bigger the force will be. So if you compare the diagram on the left and also on the right. So the nail here is the pivot. And if we look at diagram number 1, the distance between the force and the pivot is a lot less compared to diagram on the right. And therefore, in this diagram here, you're going to have more turning effect, and which is common sense. We don't actually apply our force here. We try to apply our force at the handle to create the biggest turning effect on the spanner. So that's the second factor. And the third factor is that the moment of the force will be greatest if it acts at 90 degrees to the object it acts on. So to illustrate this, I have a crowbar and a stone. So as compared to, this is position 1, position 2. If we were to apply the force at position 1, we're going to have a bigger force because it is closer to 90 degrees. All right. So position 1 is going to have the greatest turning effect if you apply the force here. So that's the three factors that involve the magnitude of the force, the distance between the force and the pivot, and also the angle which the force is applied. So another real life example of the moment is that usually in a wheelbarrow, you have a long handle because this can increase the distance between the force and also the pivot, which turn will create more lifting force. All right, so how do we calculate moment? Here we have a formula. Force multiplied by the perpendicular distance from the pivot. And that's, in order to explain this, I have a working example here, which asks us to calculate the moment of a force. And in order to do this question, we can just plug in the formula. Fm moment equal to F times perpendicular distance. And the reason this 2 meter here is called perpendicular distance, because if you compare it with the force, it is exactly 90 degrees. Perpendicular means 90 degrees, and that's the perpendicular distance. To calculate the moment, you just have to put in 40 Newton as the force, and 2 meter in the distance, we'll get 80 Newton meter. And that's our turning effect. And that's the answer. So when it comes to this chapter, a very important keyword you need to know is called equilibrium. So now we know that something can turn, but something like a seesaw, they can turn both ways. And it's important to know how to create an equilibrium so that it becomes like that. It doesn't move anywhere. And for something to achieve equilibrium, two conditions needs to be applied. The force must be balanced, and the turning effect must also be balanced. And in this seesaw example, what it means is basically the downward force has to be equal to the upward force. And also the clockwise movement, as represented by the pink color arrow here, has to be equal to the anti-clockwise movement. as represented by the blue arrow. All right. So to show you what it means, I have a real life example here. So we have a girl sitting 2 meters apart from the pivot. So the row is basically the pivot, and she's weighed 500 Newton, whereas the father is 800 Newton. And the question asks for where should he sit in order to have an equilibrium. So let's try to solve this question. And remember, the condition for equilibrium is that clockwise moment has to be equal to anti-clockwise moment. So in our case here, the father, that on the right, is exerting a clockwise moment when he sits down, whereas the daughter here is exerting an anti-clockwise moment when she sits there. And how do you get the clockwise moment, right? Again, moment formulas, recap, force time distance. So the clockwise moments, we know that that is 800 Newton. It's just that we don't know where he should sit. So it's going to be 800 multiplied by d, and that's the clockwise moment. And the anti-clockwise moment is going to be where the daughter sits. The daughter is 500 Newton, and she sits 2 meters from the pivot. So in other words, her moment, the moment that she creates, is going to be 500 multiplied by 2. So it's going to be 1000 Newton meter. And now we're going to let anti-clockwise to be equal to clockwise moment in order to find the unknown, the distance. So it will be 800, let's change another pen, 800 d equal to 1000. And to find d, we just use 1000 divided by 800, you got 1.25. And then unit should be meter because we're using Newton meter here. So our answer should be 1.25. And that's how we solve it. We basically just let the clockwise moment to be equal to the anti-clockwise moment. And that's the solution. The anti-clockwise moment, that's the clockwise moment. And then we find the unknown. So let's look at example 2. The beam below is 2 meters long and has a weight of 20 Newton, and it is pivoted as shown. A force of 10 Newton here acted on the right. And then what they're asking, what force should, what should be the force on the left be in order to have equilibrium, all right, balance. So one side note for this type of question is that you need to remember that the rod here also exerting a moment here, specifically the center of the rod. So this is the central. And therefore, even though it's not stated in the question, we need to assume that there's 20 Newton, which is the weight of the rod, exerting a moment here and the pivot, which is here. Because currently the center of the rod is not at the pivot. Therefore, it is also exerting a moment here. This is when we need to take in extra consideration. And beyond that, we can just do basically the same thing as we did. In order to find what is F here, we need to first calculate what is the clockwise moment, followed by what is the anti-clockwise moment. And let's do the clockwise moment. So the first one, let's do this one and this one. The moment exerted by the by the rod, it will be 20 Newton. M equal to F times D. So we're going to be 20 times 0.5. You're going to have 10 Newton meter. So that's the first clockwise moment. And the second clockwise moment is going to be, I run out of space. Let me rub this off. It's going to be, let's do M2, 10 Newton as the force here. But the distance between this force and the pivot is not 1, it's in fact 1.5. So I'm going to multiply 10 by 1.5 here. So I have 15 Newton meter. In other words, I can say that my total clockwise moment is 25 Newton meter, 10 plus 15. And let's look at the anti-clockwise moment will be very simple. Again, F times D. Since we don't know what is F yet, I can just write it as an unknown followed by 0.5. So to write it better, it should be 0.5 F. Now, in order to find out what is the value of F, all I need to do is that can let 0.5 F to be equal to 25, and then F would then be equal to 25 divided by 0.5, we get 50 Newton. So this force here should be 50. And that's how we solve it. Basically, we calculate the clockwise and anti-clockwise movement and then find out what is the unknown for this question. Sorry, my camera just fell down. And that's the answers. All right, so now we have to do a series of questions that shows how the clockwise moment has to be equal to the anti-clockwise moment. Remember, the second condition for something to be in equilibrium is that the force has to be the same, meaning downward and upward force must be the same. So let's look at a follow-up question here. Using the answers from the previous question, which is this one, measure the total downward force. So we can just add them up. 50 plus 20 plus 10, we're going to have 80 Newton. That's it. The answer is 80 Newton. And now, follow-up question, mark the upward contact force with the letter R on the diagram above. So in order to know what's the contact force, we have to see where the pivot and also the bar contact. And in our case here, this is where the upward contact force will be. And follow-up question, state the upward contact force. Because we know the theory, downward force has to be equal to upward force. Therefore, my upward contact force here is going to be equal to 80 Newton, which is the total downward force that we calculated. And that's about it, 80 Newton. So let's look at the last work example question to further understand what is going on. What we need to do is to calculate where should the 125 loads be placed in order for the ruler to be balanced. So now the ruler is placed in the center. And what we need to find is basically how far should the force be. And again, we can use the clockwise and anti-clockwise movement again. So first of all, we can calculate the clockwise moment. So I'm going to get what I have. So the first one is 56 Newton multiplied by 0.34. That's the first clockwise moment, which I'm going to get 19.04 Newton meter. So that's the first one. And M1. And for M2, I'm going to have 125 Newton, but I'm not sure where should I put it. So I'm going to leave it as unknown. So I'm going to have 125 D. Whereas I can actually calculate the anti-clockwise moment by using 76 multiplied by 0.44. So I'm going to do this. I will have 33.44 Newton meter. And now all we have to do is just let the anti-clockwise moment to be equal to the clockwise moment. So I'm going to let 33.44 equal to 19.04 plus 125D. I'll make D the subject and then move everything to the left. And then I'll just calculate what is the value here. I'll get 14.4 divided by 125. And the final answer should be 0.1152 meter. And that means this 125 Newton should be placed exactly at 0.1152 meter for this ruler to be balanced. And here's the answers. You can pause the video to look at it if you feel like I'm speaking too fast. All right, so the second question is, what should be the upward force? We already know upward force has to be equal to downward force. That's why we just have to calculate what is the total downward force that we have. So it's gonna be 76 plus 125 plus 56. And I'll have 257 Newton in total. So that will be the upward force required to lift this up, which is correct as shown in the solution. All right. So by the way, if you're watching here and you would like to get the slides here, you can always visit my website to purchase it, either for personal revision if you are a student, or if you're a teacher, you want to use it in your classroom, you can also purchase it. And your support is greatly appreciated. All right, now let's move on to center of gravity. And the definition is that it is the point of an object where the force of gravity appears to act. So in this pens here, there's something called the center of gravity, and it's usually the center, meaning the force of the gravitational force will likely act at the center of this pencil here. So to give you more example, here I have a ball, a sphere, cube, pencil, body, and the center of gravity is usually at the center. And to find the center of gravity, you can just draw a dotted line across the object. And the key thing is that the point which the dotted line intersect will be the center of gravity of the object. And in order to find the center of gravity for a regular shape, like in this diagram, here's an experiment that you can do. Just pop 3 holes or more holes into it, and then try to hang it using a thread, and let it be, and then draw out the dotted line, and do it for different holes. All right, and then once you got all the dotted lines, the point which all the dotted line intersect will be the center of gravity of the irregular shapes. And that's just one thing that is in your syllabus. All right, so now I'm going to discuss how this center of gravity thinks is going to affect stability of something. So I know there are a lot of words here, but for now you can just listen to me. So on the leftmost diagram here, the reason this box is remaining stationary is because the upward contact force, the pivot here, is equal to the gravitational force acted on the center of gravity of this object. But if I were to tilt this rectangular shape a little more to the right hand side, but not too much, you'll see that now the center of gravity is at the left of the contact force. So this is, we can also call this the pivot. Now, because the center of gravity is acting this way, and it then creates an anti-clockwise moment, and this will cause the rectangular shape to be back to its original place. That means it won't fall down, it will just go back to its original place. Whereas if I were to tilt a little bit more, like in this condition here, and then I release my hand. So we all know that the rectangular shape will fall, but why is that? And this is because now the center of gravity is acting towards the right of the pivot, which creates a clockwise moment. And when there is a clockwise moment, means clockwise turning effect, this rectangular shape will fall. And that's basically what the slide is trying to explain here. Okay, so let's look into some puzzle question for a moment before we end this video. Here we have a tower crane being used to lift a heavy load. So there's the load. In order to maintain equilibrium, so that's keyword. Equilibrium means clockwise equal to anti-clockwise moment. The total weight has a counterweight W on the right hand side. The question is, what is the weight of the load being lifted? That means what is the weight of this? Should it be less than, greater, or the same as W? So now we know that clockwise moment has to be equal to anti-clockwise moment. Now, so W here, you can see that this is the pivot, because that's when everything turns. And the distance between the pivot and also the weight, L2, let's do it L2, is a lot greater than the distance between this counterweight between the pivot. So if we were to write this equation, it's going to be X, let's do it X. X multiplied by L2, the anti-clockwise moment, is going to be equal to L in W. Okay, and this is the counterweight. They're asking what should this be? What should X be? Should it be greater than W or should it be smaller than W? Now, a very important thing is that if you look at L2 and L, L2 is a lot bigger than L. Okay, so this one is bigger and this one is smaller. And in order for both equations to be equal, W has to be greater than what is X. So that they can equal each other up. So when they ask what is the weight of the load being lifted, so X clearly it has to be lighter than W. And that's how I come out with the conclusion. So the answer should be B. So try to think a little bit more. Just put in some hypothetical value. It should find out that this is true, and the answer should be B. Great. So let's move on to the next question. This is relatively simple. Which point label is the center of mass of the cardboard rectangle? To get, of course, we know we can draw the symmetry line. You see that after you draw all the lines, this is the point which all the dotted line intersect. So the answer is C here. Okay. So let's move on. In which position is the wardrobe in equilibrium, meaning it won't fall? So let's investigate one by one, shall we? So let's look at the pivot, diagram A. So this is the pivot, and this is the center of gravity of the cupboard, meaning there's a force acting towards the left of the pivot. So in this case, we can say that there is a anti-clockwise moment here, and therefore this will not be in equilibrium. So question 2, again, this is the pivot, and the center of gravity is acting to the right of the pivot, meaning here we have a clockwise moment instead. That means it will turn, it won't be in equilibrium. So that's not correct too. And let's look at C. So that's the pivot, and the center of gravity is acting here, aligned with the pivot. So let's assume that there's no clockwise moment and anti-clockwise moment. So that's the correct answer. But I also want to check out whether D is correct or wrong. So here we have pivot, and then again, the center of gravity is acting at the right-hand side of the pivot. So again, I have a clockwise moment, so this will not be in equilibrium as well. So my final answer is C. And yeah, as shown in answer, this is correct. Fourth question, the diagram each. By the way, I'm showing past two questions so that you can apply what you learned into solving question that is required by IGCSE. Okay, let's continue. The diagram each shows a beam resting on a pivot, and the pivot is the center. Which of the beam is in equilibrium? Again, we have to investigate one by one. So we know that in this diagram A here, we have an clockwise moment here, another anti-clockwise moment here, represented by the blue color, and here 400N acting upwards. So we're going to have a clockwise moment. So you can see that we have two clockwise moments and one anti-clockwise moment. Therefore, they're not equal. Second one, 400 Newton acting upward. So we're going to have an clockwise moment. And the other one is that we're going to have an anti-clockwise moment. All right, so it seems like now they are equal. But then we see that the forces are acting upward. With the contact force also acting upward, we will have an imbalanced downward and upward force. And therefore, this is also not the answer. So the third question looks like it is C. So we have a clockwise moment, and again, another clockwise moment. But we have no anti-clockwise moment. This means that the moment, they are not equal. Last but not least, we have a clockwise moment and then so an anti-clockwise moment. So 1, 1, and this is correct. So the answer is donkey because the clockwise and anti-clockwise moment are equal, and also the upward and downward force are the same. And the answer should be donkey. Thank you. So last two questions. A plank rests on two supports as shown in the diagram. The plank is in equilibrium. Three forces acted on the plank. Which statement is true? So because they are in equilibrium, let's look at A. The upward force is greater than downward force. This is incorrect. Otherwise, it will not be in equilibrium. The resultant force on the beam is 0. Correct. The resultant moment is also 0. So that's the correct answer. Force and moment is equal to 0. But let's look at what C. The resultant moment is 0, but the resultant force is not 0. So it's not correct because we need two conditions to be true. So all three forces are equal in size. You can't really say that because we don't really just care about force. We also care about the direction of the force, which is the turning effect. All right. So the answer is B. And here we have a paper 4 question, the last question for today's video. And So let's try to understand what it's saying here. The distance PQ is 100 cm, meaning from here to here, it is 100 cm. And therefore here should be 50. I'm just writing it down, it might be useful. And the mass of the meter rule is 0.12 kg, and its weight is W. On the diagram, draw and label an arrow to show force W acting on PQ at the center of mass. So again, the center of mass is usually at the center of the object. So I can just draw a W here. So I'm going to use a pink color to write my answer. So that's my W. I got 1 point for that. And an arrow to show the force R acting on PQ at the pivot. R is the force at the pivot. So something we do just now. I can just write here, another point for me. Now, we have answered first question. By taking moments about pivot, calculate what is F. All right, so now we need to calculate what is F. So in order to do that, again, we need to let clockwise moment to be equal to anti-clockwise moment. But first, let's calculate what we have. So we have three forces here. 1, 2 acted by the rod, and also 3. So the clockwise moment will be the only one here, which is acted by the center of gravity. So we know that the force acted on the center of gravity is actually the weight of the rod. And first calculate the weight. The weight, I'm going to use W equal to mg. And for simplicity's sake, I'm going to assume G equal to 10 for this question. But then in your syllabus, you should use 9.8. But let's use 9.8 instead. Okay, 0.12 multiplied by 1.8, 9.8. I'm going to get the weight of the rod. So which I will get 1.176 Newton. So in other words, I can say that 1.176 Newton is acting here in the center of the pivot. So my clockwise moment is going to be 1.176 Newton, and the distance between the center and also the pivot is 40 cm. But in this case, I want to convert it into Newton, meter. So I'm going to have 0.4 meter. And if I plug that into calculator, I will get 4704 Newton meter. And that is my clockwise moment. And let's look at my anti-clockwise moment. Let's do this. The one we have, it's very easy. We can just do 0.5 Newton multiplied by 0.1 meter. I'm converting this to meter here. So I will have 0.05 Newton meter. At this point, you might be curious, the third one, shouldn't this be clockwise moment because it's on the right? But if we look at the direction of the force, it's acting towards from here to here. Okay, so it is actually an anti-clockwise moment. So I'm going to do ACW to the second one. We don't know what's the forces, but we know the distance, which is 0.9 meter. I'm going to have 0.9 F. So now, in order to calculate what is F, we let clockwise moment equal to anti-clockwise moment. So 0.47 equal to 0.05 plus 0.9 F. And let's make F the subject. 7 minus 0.05, and F is equal to 0.42 divided by 0.9. I'm gonna do this, and I'll get 0.467 Newton. So the answer should be Newton. All right, so the next question asks us to calculate what is R. Because they are in equilibrium, we also assume that the downward and upward force are the same. So in order to calculate R, we need to calculate the total downward force. Okay, so downward force, here we have 0.5 plus 1.176 plus 1.176, you get 1.676 Newton. Whereas the upward force is not just going to be R, but R plus what we calculate just now in the question. So it's going to be R plus 0.467 Newton. So let's try to make our upward and downward force the same. So you're going to get 1.676 equal to, I run out of space here. So I'm just going to let this equal to this. So my R is equal to 1.676 minus 0.467. And then now I should be able to get my answer, 1467. I get 1.2 Newton. And that's about it. So my R is 1.2 Newton. I apologize for not putting enough space in it. But I actually done it beforehand to let you see the full answers. And I believe this is neater. So try to pause the video and try to solve it yourself, because turning effect moment is not something that is easy to learn. And with that, I will conclude this video. And in this chapter, we learn about moment, turning effect, what factors affect the turning effect, and how we can calculate moment based on different scenarios. And I hope you enjoyed this video, and I'll see you in the next video. See you.